studying. He learned learned English in the US, but before moving to the US, he already had discovered philosophy. And apparently, he discovered philosophy in relation to the problem of the existence of God. Is there a God or not? And as he himself tells the story, he embraced atheism the day before his bar mitzvah. Yes. Which just a great sense of timing, when you're going to do the most important things in your Jewish life, you decide that there's no God. That's it just tells you a lot actually about what kind of man and thinker Adolf was. From 1944 to 46, he served in the U.S. Army at the end of the Second World War. And he was part of something that is known as the Ritchie Boys. Maybe not all of you know what the Ritchie Boys are. They were a group of intelligence officers whose main job, often of German families, whose main job was to interview German officers and Nazi officers. So if you've known Adolf Grünbaum, he was a small man. You can totally imagine him. But extremely bright, extremely brilliant, interviewing and getting the truth about the German officers and the Nazi officers. Actually, an image which I find extremely vivid. He got a master's degree in physics and a PhD in philosophy from Yale after the Second World War, and then got hired by Lehigh University, where very quickly in 5 years was promoted to full professor. Just tells you how already widely recognized as a very bright mind. In 1960, the University of Pittsburgh, our university, was extremely likely to steal him from Lehigh. And he was the first Andrew Mellon professor. We have an Andrew Mellon professor right here, David Wallace, who inherited the chair from Adolf. He was the first Andrew Mellon professor here at the University of Pittsburgh. And he quickly became the most prominent philosopher of physics of his generation. He published books such as Philosophical Problems of Space and Time, which was at the time an extremely influential contribution to the philosophy of physics. His work was not limited to the philosophy of physics. He also worked on the philosophy of religion, and indeed the question of the existence of God was a constant topic of thinking throughout his life, and he was a militant atheist. And later on in his life, he worked on psychoanalysis and was actually an extremely dedicated opponent of psychoanalysis, not only from a theoretical point of view, but from a practical point of view, trying to do his best to undermine talk therapy here in Pittsburgh. Somewhat more controversial, but also really exciting aspect of his intellectual life. Someone who actually thought the philosophical and theoretical commitments had to be translated into action, changing what people were actually doing. We're not only remembering Adolf because he was a great philosopher, even so he was. We're also remembering him because he literally built philosophy here at Pitt. I think Pitt would not be such an extremely wonderful place to do philosophy and philosophy of science without Adolf Grünbaum. He's the man who, when he was hired, just built up what we now are benefiting from. He founded the Center for Philosophy of Science in 1960. He created the annual lecture series, and well, he's actually part of the 55th annual lecture series. And he was the director of the center and then the chair of the center for many years until actually he was a chair until the end of his life in 2018. So in honor and memory of his legacy and his contribution to philosophy and also to Pitt as an institution, the center has established, after his death in 2018, his lecture, the Grünbaum Memorial Lecture. And every year, we welcome a scholar to give a lecture in Adolf's name. The lecture was established thanks to a gift from his daughter, Barbara Grünbaum, and her family. So we're extremely grateful to Barbara Grünbaum to have this opportunity every year to commemorate Adolf's memory. I think that's a wonderful thing to do for someone who's given so much to philosophy, but also to the University of Pittsburgh and the center. And so this year we are delighted to that the Adolf Grünbaum Memorial Lecture will be given by Professor Wen Myrvold. Wen, as many of you might know, is a professor of philosophy in the Department of Philosophy at the University of Western or Western Ontario. I think it's not quite settled, or is it Western?
It's the University of Western Ontario.
It's the University of Western Ontario.
Yes.
All right, so the University of Western Ontario is a philosopher of physics who has written on many aspects or many topics within the philosophy of physics. He was a former fellow here at the center in 2015. So it's actually quite a nice occasion to welcome you back. He's the author of the acclaimed book, Beyond Chance and Credence, a theory of hybrid probabilities. I know philosophers of physics here at FIF have read the book quite closely and discussed it. I know they had a reading group on the book a few years ago. He's also the editor of special issues and a book, including Quantum Reality, Relativistic Causality, and Closing the Epistemic Circle. He's published really widely in the philosophy of physics, in the best journal in philosophy of science and philosophy more broadly. So I won't go through the long list. I've already been speaking for far too long. But in any case, thank you for accepting our invitation to be the Grünbaum Memorial Lecture. This year.
Thank you, Edward. I must say, it's great to be back. As Edward mentioned, I did spend a term here as a center fellow, and I was also a visiting professor in HPS in 2011. And in fact, my office was next to Edward's at the time. And my time at Pittsburgh has been like, it's always incredibly intellectually vibrant and wonderful. And this past few days have been really full. It's a great honor to be invited to be part of your annual lecture series, and even greater honor to be invited to be the Grünbaum Memorial Lecture. So thank you, Edward, for that. Yeah, Adolf Grünbaum was actually part of my introduction to philosophy of science fairly early on. I think when I was an undergraduate, I read parts of his book on philosophical problems in space and time. I don't think I understood everything at the time, but it was absolutely clear that there's like interesting stuff to do. And I think it helped motivate me to go into philosophy of physics. Okay, so thank you everyone for coming. Okay. So when I started grad school almost 40 years ago, debates between scientific realism and anti-realism had already been major topics in philosophy of science for quite some time. The first three books in the upper left were books that were assigned reading in a graduate seminar I did at Boston University, and they're ongoing. And this is just a small sample of work, and if you can read the names, there's an impressive array of very eminent scholars, people there, many of whom I regard as friends, people I respect a lot. There have also been skeptical voices. In the same issue of Dialectica in which John Worrell's famous structural realism paper was published, there was also a paper which I think deserves to be more attention, stemming from the same conference at Neuchâtel that Worrell's paper is from, called by Howard Stein, and he says, yeah, it's called Yes, But Some Skeptical Remarks on Realism and Anti-Realism. And what he says is this paper argues that the much discussed issue between scientific realism and instrumentalism has not been clearly drawn. And the closing line of that paper is where I get my title from. His last line is, yes, realism, yes, but instrumentalism, yes, only, no, only to anti-realism. Okay. Just want to look ahead at my conclusion. I love mystery stories, but I don't necessarily think that philosophy talks should be mystery stories. For most of this time, in my career, I've thought I was a scientific realist, and now I don't think I am. Not that I've gone over to the opposing camp, I'm not betraying my friends who are scientific realists, but I now think there is no such thing as scientific realism. Okay. But there are various forms of anti-realism which we should reject, and that's why my title is No Only to Anti-Realism. So as a background, a lot of you are familiar with all these discussions about scientific realism and anti-realism, largely have to do with the status of unobservable things that are posited in science. And there's a long history of that, of postulating unobservable stuff behind the scenes that accounts for the behavior of the things we observe. It goes back at least as far as the ancient Greeks, and it probably goes back to prior to written record. So, for example, in Plato's Timaeus, Timaeus gives an account of atoms which are shaped like the Platonic solids. In ancient astronomy, people talk about crystalline spheres carrying the planets. In the 17th, 18th, and 19th century, various humors and ethers were postulated. Phlogiston famously is a postulated stuff that has been debated in the realism and anti-realism stuff. Caloric, supposed to be the substance of heat, atoms and molecules, protons, electrons, neutrinos, other members of the particle zoo, dark matter, etc. So the question of scientific realism and anti-realism is, what should our attitude towards this stuff be? So Timaeus himself in the dialogue is not presented as saying, I think this, I'm sure this is the way things are. He presents it as a likely account or a likely story. And throughout the history of science, we do find various scientists expressing reserved attitude towards these postulate unobservable stuff. And some people in the late 19th century, faced with a multitude of various unobservable things, atoms, molecules, luminescent ethers, etc., adopted a uniformly anti-realist attitude towards them. So the view is that it's okay to talk about such things, but you shouldn't take it too seriously. These things may be aids to systematizing our thoughts about observable phenomena, but we should refrain from committing to the actual existence of things. It's enough if they help us understand relations between observable phenomena. All right. Okay. I think that goes too far. People are right to be skeptic about excessively speculative stuff, speculation unmoored from empirical evidence. A blanket prohibition on accepting the existence of unobservable entities is unwarranted. And my claim is that anti-realism is fueled by an inadequate appreciation of the power of empirical evidence to support a theoretical hypothesis under favorable circumstances. By the way, I've been using this word unobservable. I haven't said very much about what the distinction between what counts as observable and unobservable is, and I don't think I have to. If someone like von Frossen is going to base an anti-realism on that distinction, they need to say something about what that distinction is. If someone who doesn't think that distinction needs to carry any weight doesn't have to be very precise about it. And I actually think that the way it's actually used in science is context dependent. So, for example, some people might be looking at data from astronomical phenomena, and on the basis of that, inferring a distribution of dark matter. Then in another context, someone might have a theory of galaxy formation, including both visible matter and dark matter, and they might make predictions about the distribution and compare it to the observed distribution of dark matter. Okay. I'm going to start with some theses that I think should be non-controversial. There's a lot of philosophers in the room, so if you're a philosopher, you know that even if something should be non-controversial, it rarely is. I think it should be totally non-controversial. It is sometimes possible to draw inferences that take observed phenomena as evidence for conclusions that are either accepted or taken to be highly credible, with all degree for fallibility. There's a difference between acceptance and high credence, but for the purposes of this talk, it's not going to be matter too much. About matters that have not yet been observed. So, for example, I've got an app on my phone that can tell me where Mars is going to be in the sky 10 years from now. Right? Yeah, the astronomers are really, really good at calculating, and predicting trajectories of planets. And of course, we couldn't live unless we accepted this, unless we are making inferences based on what we have observed to what has not yet been observed. The same sorts of, I'm not the first person to say this, but I think it's true. The same sorts of patterns of reasoning using those inferences can, under favorable circumstances, lead to conclusions about unobservables, which are at least as well supported as some of the conclusions we accept about the observable but not yet observed. Right. There's a word missing. You should say not yet observed. And those do need to be evaluated on a case-by-case basis. Sometimes understanding the bearing of evidence on hypotheses is a very delicate matter. But I think it follows from these theses that I think should be non-controversial is in the absence of a principled reason not to accept conclusions about unobservables, we should, in some cases, accept those conclusions. And then the divide between the realists and anti-realists is whether or not there is such a principled reason. So I actually think that everyone, include anti-realists and realists alike, should accept everything on this slide. And these conclusions include conclusions with atoms, molecules, subatomic particles, etc. And I claim there is no principal reason not to accept such conclusions. One of the things, now if I'm going to make that sort of claim, I'm going to have to address some of the arguments for that. In the literature, the strongest argument that in many people's eyes is some sort of pessimistic meta-induction. It's a routine in both the realist and anti-realist camps to say that the history of science poses a challenge to realism. And so I will be talking about that. Right. Okay. Now, what I just had on the previous slide might sound to some people like scientific realism. But I think a mere recommendation to allow one's belief to be responsive to the evidence coupled with an absence of a prohibition on accepting the existence of unobservable stuff doesn't strike me as worth dignifying with an ism. A mere absence of a prohibition is different from a substantive philosophical position of the sort that people usually associate with scientific realism. And people who advocate versions of scientific realism tend to say try to formulate very sweeping things about what sorts of unobservables we should accept and what sorts we don't. Right? And I actually think that we can't say anything better than believe in what you have good evidence for. I don't think anything stronger can be defended or that it needs to be. Say in a moment why I think it's better not to actually think of what you're doing as defending some version of scientific realism. Okay. So no only to anti-realism, but only that. Okay, I just said that I don't think there is anything like scientific realism. And there's all these books out there by eminent scholars, some of whom are close friends. So, if I go to my library and I pick up one of these books and take in my hand some volume advocating some version of scientific realism, dear Stathis, Hessuk, Michaela, I could have brought 20 books if I wanted to. Do I cast them to the flames as containing nothing but sophistry and illusion? No. Because I think there's actually a lot going on in those books which is very valuable that we don't have to think about as involving a clash between two camps, realism and anti-realism. And I want to quote something that I learned from my teacher in grad school about intellectual virtues. Abner Shimoni taught his students, that intellectual virtues, just like Aristotle's moral virtues, are means between opposing vices. And Abner was, in particular, was concerned about finding the mean between excessive credulity, like proposing a theory and falling in love with it and believing it without good reason, and excessive skepticism. Right. And so what I want to say is the reason I don't want to cast those books to the flames is that even if I don't think we should think of them as being, they're being rival camps, the realists and the anti-realists, or realists and the and instrumentalists, we can think of these as extended discourses and exploring where that virtuous mean is between excessive credulity and excessive skepticism. And that is an important task for everybody. And other people have said similar things. At lunch, I promised a quiz that I expect the Italian members of the audience to get. So the question is, who is that? Luana, I know you know. So John Chakravarty talks about the realist tightrope. He says, if realism is purchased at the cost of believing all is nothing, it's largely empty. If instead realism is made more substantial by licensing ever greater quantities of substantive belief, it runs an ever greater risk of, for example, falling prey to concerns arising from theory change. It is no easy feat to get the balance just right. As I mentioned earlier, realists and anti-realists alike think that there's a substantive challenge to realism from the history of science. Okay. And Peter Vickers, in his recent book, points out, well, this is a balance too that anti-realists have to get. Like, the anti-realists don't want to be skeptical about all science; they want to be skeptical about parts of science. And Kyle Stanford himself talks about a middle path. Right? There's middle path realism and middle path anti-realism. Okay, which avoid the screen. And I think all of that is right. There is an issue of striking a balance. But I don't think tightrope is the right metaphor for two reasons. One is a slight misstep in the direction of excessive credulity or excessive skepticism is not a disaster. It can be corrected. And for that, the reason is you're not alone. You're not. Science is not something that people do as isolated individuals. It's something that is done as in research communities. And you just expect a sufficiently diverse community to include some people who sort of err on one side and some people who err on the other side. And actually, I think that that's a good thing. I think it's a good thing for a scientific community to contain both framers of bold conjectures and skeptics who say, okay, you know what, convince me. Peter Vickers, in his book, mentions a professor of geology who was very dismissive in the early days of plate tectonics. And he said, show me a force that can move the continents. Right? Probably not, I don't think that's unreasonable. And I think that that is a challenge that the advocates of plate tectonics needed to accept, and they did accept. By the way, we have a tendency to take something that has been accepted and then sort of look back and honor the early adopters. And you would expect in most cases, actually, the early adopters are probably erring on the side of excessive credulity. Right. Okay. All right, so I said the big challenge. So I'm not saying I'm a scientific realist, but I'm saying no to anti-realism. And that does mean that I have to confront what a lot of people think as the best argument in favor of anti-realism. And it goes by the name of the pessimistic induction or the pessimistic meta-induction. And the claim is that the history of science involves radical shifts in widely accepted theories involving radical shifts in ontology. And then the inductive conclusion is we should expect it is that many, or maybe most, all of our own currently accepted theories to suffer the same fate. Okay. Now, even if I'm not thinking of the enterprise as a debate between realists and anti-realists, and I want to frame things instead of in terms of finding the virtuous mean between excessive credulity and excessive skepticism, I can read those arguments as claims to the effect that scientific communities of the past have routinely erred on the side of excessive credulity, and that this should make us temper our own credence in our currently favored theories. We should be worried about whether we're doing that too. There's a version of this in Poincaré's Science and Hypothesis. It's not Poincaré's own argument. He attributes it to les gens du monde, the people of the world, the educated public in the most recent translation. And he regards it as exhibiting superficial skepticism. And I'm mentioning that because sometimes in the literature, this argument is attributed to Poincaré himself, but it's not. It's not his. Right? He says the educated public is surprised to see how short-lived scientific theories are. They see them abandoned after a few years of favor, the wreckage of one theory piled on the rubble of another, anticipating that today's fashionable theories will soon give away, and from this they conclude that these theories are completely futile. He says, no theory seemed more solid than Fresnel's, which attributed light to the motions of the ether. Nevertheless, we now prefer Maxwell's theory. I think that those last pair of sentences has been misunderstood in the scientific literature. I think a lot of people don't realize there's a pun there. Fresnel's ether was an elastic solid. And also, some people talk as if the contrast between Fresnel and Maxwell is a contrast between a theory with an ether and a theory without. But it's not. It's just whatever Maxwell's ether is, Maxwell thought it likely that magnetic fields were associated with some kind of vortices, and so it can't be a solid, it has to be a fluid. Okay. A very influential version of the pessimistic meta-deduction comes in John Worrell's paper on structural realism, which I've already mentioned, published in the same issue of Dialectica that the Stein paper is published in. And John Worrell does regard himself as advocating a version of realism, but he thinks he has to take the pessimistic induction seriously. The title of the paper is Structural Realism, Best of Both Worlds. He wants a position that does justice both to the no miracles argument in favor of realism and the pessimistic meta-induction against it. And so he gives a version which has to do with the history of optics from the 18th to the 20th century. And because it's been so influential, I'm going to discuss that version. I have neither the time nor the competence to make a sweeping generalizations about the history of science in all fields, but I can say something about the history of optics from the 18th to the 20th century. Okay, so he talks about Newton and his 18th century successors having a particle theory of light. Newton's Optics was published in 1704. In the early 19th century, in the 1820s, wave theory was revived. On this version, light is a transverse vibration in an all-pervasive elastic solid, as I mentioned before, the luminiferous ether. Then he mentions Maxwell's electromagnetic theory of light. And there again, light is transverse vibrations in a different sort of ether. And then here's what Worrell says about that. Maxwell, as well known, strove manfully to give an account of the electromagnetic field in terms of some underlying mechanical medium, but his attempts and those of others failed, and it came to accept that the electromagnetic field is a primitive. Worrell doesn't say when that came to be accepted, and I'm going to talk later about that. But the way he phrased it has misled people into thinking this happened during Maxwell's lifetime. And so people following Worrell have attributed to Maxwell the idea that light is the electromagnetic field is a self-standing entity in otherwise empty space and there's no ether. Okay. Then the early 20th century, we saw the advent of light quanta or photons. He doesn't take it further into in that particular article to quantum electrodynamics, which really was formulated in the 1940s and 1950s. Okay. So when I read things like this, and there's lots of examples of things like that in the literature, the picture that seems to underlie that, sometimes implicit, but sometimes completely explicit, is that the story is a story of punctuated equilibrium. That for a time there's near consensus on theory in the basic ontology of the world, and that this consensus is interrupted by occasional revolutions involving radical shifts of theory and ontology. So Worrell, for example, he mentions Newton, doesn't mention anything else that happens in the 18th century. No one is mentioned until Fresnel in the 1820s, right? And according to this picture, most of the time, scientists are working with something like a completed theory. Maybe the details have to be worked out, but a more or less completed theory. And the process of theory construction occurs fairly rapidly during times of revolutionary shifts. Okay. And I think where that picture comes from is from sort of textbook snippets that you find in physics books and things like that, where only a few key figures are mentioned, forgotten rival theories or go unmentioned, and the often complex and lengthy process of theory construction is submerged. What I want to claim is, at least in this case considered, as I said, I don't have neither time nor the expertise to make sweeping generalizations about the history of science in all fields. But if you actually look at the history of optics from the 18th, 20th century, it is actually a long story of theory construction. At every point of which multiple avenues are being explored, and no, there's nothing that anybody regards as a completed theory. I further claim that if you make distinctions that are often elided in the realism and anti-realism between what, in the scientist's own judgment, at the time, is taken to be firmly established, and what, in the scientist's own judgment at the time, is taken to be conjectural, and what, in the scientist's own judgment, is thought to as playing a heuristic role with no commitment to representing something real, then it's actually not so easy to find anything that was widely taken to be firmly established but is now rejected. Okay. And in particular, the standard story that you get in the realism, anti-realism literature, with some exceptions, the one person who really does justice to this is Sathis Psillis in his book. Right? Standard story, I want to claim, misrepresents historical reality at every step. First of all, everyone says Newton was a particle theorist. You say it over and over again. Now, Newton actually, if you actually read Newton, and this is true not only of the optics, but of the Principia, he's very good at distinguishing between the things that he thinks are firmly established and the things that he regards as more conjectural. Just read the last few paragraphs of the Principia about what he actually thinks he knows about gravity, right? And in the optics, he explicitly distinguishes between different sorts of material. There's reports of experiments. There's what he labels propositions, which he regards as established on the basis of the experiment. And then there's a lot of conjectural stuff, which is at the end under the heading of queries. The conjectural stuff, he's not even expressing in the form of declarative sentences. He says, does it not seem likely that? Right? And there's like lots and lots of stuff like that. Now, of course, he does think that this is suggested, but he is signaling that it is somewhat speculative and conjecture by framing it in the form of a query. Okay. It's one thing that people don't mention, that in these queries he speculates about an ether that light creates vibrations in. So there, right. Something I forgot to say is, in the first edition of the optics, there's no mention of light consisting of a stream of corpuscles. None. That comes in like 2 years later. There's a Latin translation where he added some more queries, and it's there that he says, does it not seem likely that light consists of a stream of corpuscles? And then he just adds to the queries as successive editions goes, but he never turns that into a declarative sentence. Right? Okay. Fresnel's conception of the ether was advanced by Fresnel very tentatively, and it did not gain widespread acceptance. Contrary to what is suggested, but has been suggested to some by what Worrell says about Maxwell, Maxwell and his immediate followers did not think of the electromagnetic fields as disembodied, self-standing things. And I want to illustrate what I'm saying just by a few quotes. And I am working on a paper, and it's becoming longer and longer because I actually do want to back up what I'm saying with evidence, and then just adding more and stuff like that. And actually, this issue touches on so many different things. I'm starting to worry that I'm going to have to turn it into a book, right? So this is D'Alembert. He wrote a article for the encyclopedia. He's one of the encyclopedists on light. And he canvasses both the people working in the Newtonian tradition with light as a stream of corpuscles, and people following Descartes and Huygens, who thought that there was vibrations in some kind of medium. And what he says, it must be admitted that neither of these two opinions is proved, and the wisest answer would be perhaps to say that we know nothing about it. Right? So I actually think that's given the time, that's a fairly judicious attitude. And this is an encyclopedia article, right? Okay. Fresnel, actually, I wanted to say something about this. In some of the literature on theory choice, it's routinely said that in cases where the empirical evidence doesn't determine the choice of theories, there are extra empirical criteria that are supposed to come in and make the choice. And very rarely is the option of saying, I don't know, actually considered, right? And it's never clear to me how, what the scope of these extra empirical virtues are supposed to be. Do they never, ever leave us undecided? Yeah. Do they always allow us to make a choice? Actual scientists very often say they don't know certain things. Okay. Fresnel argued on the basis of polarization phenomena that light is a transverse wave. And I think that it's worth looking at actually the reasoning there. I think that the literature, even though this is one of the prime examples in the pessimistic meta-induction literature, I think that his reasoning hasn't been fully appreciated. It really is a wonderful example of how to use experimental phenomena to draw conclusions about stuff that you're not directly observing. So he's experimenting with polarized. So basically, in a nutshell, phenomena of interference suggests that there's something vectorial associated with light, because you have to be able to add and subtract things. He did experiments with polarized rays, and he split a ray through Iceland spar to an ordinary and extraordinary ray, and he found that you can't get interference between them. And unless you rotate the polarization of one ray and so that they're polarized the same way, and then you can get interference. And that strongly suggests that whatever vectorial phenomenon is going on that is responsible in light, that polarized rays are orthogonal to each other. It's hard to see how that can be unless it's a transverse wave and not. It's easy to see how that could be if it's a transverse wave. It's hard to see if it's a longitudinal wave. Right? Okay. He proposes a medium and elastic solid ether. We all get told that Fresnel believed in this ether. Here's what he says. I will only attempt to show that the hypothesis I'm presenting is not physically impossible. and that it can already be used to explain the main properties of polarized light by means of very simple mechanical considerations. Okay, he's not saying this stuff really exists. And a lot of people were very skeptical that that sort of stuff exists, because this luminiferous ether is everywhere. I'm walking through a solid, and I don't feel any resistance. The Earth goes around the sun through this solid year after year with no noticeably slowing. It's actually not impossible for something to act like a solid when it comes to fast vibrations and short wavelengths, and act almost with very little resistance for slow motions or long wavelengths. But it is not true that there was widespread acceptance that this thing was real. Thomas Young, who was definitely on Fresnel's side when it came to light being a transverse wave, and he actually had suggested this prior to Fresnel, but he didn't really work it out. Here's what he had to say, and this is another encyclopedia article. This hypothesis of Mr. Fresnel is at least very ingenious and may lead us to some satisfactory computations, but it's intended by one circumstances which is perfectly appalling in its consequence. If we adopted the distinctions laid down by the reviver of the undulatory system himself in his lectures, he's talking about Fresnel, it might be inferred that the luminiferous ether pervading all space and penetrating almost all substance is not only highly elastic, but absolutely solid. 3 explanation points. Interesting historical question. Is this the only sentence in the entire history of the Encyclopedia Britannica that ends in 3 explanation points? 3 exclamation points. Okay. An important ethers theorist in the first half of the 19th century was James McCulloch. His work actually turned out to be relevant later for the Maxwellians, largely forgotten these days except by historians. He had his own sort of elastic solid model of the ether, and here's what he said in 1837. It is certain indeed that light is produced by undulations propagated with transversal vibrations through a highly elastic ether, but the constitution of this ether and laws of its connection, if it has any connection with the particles of bodies, are utterly unknown. And then late in his life, in a letter to Herschel, he said, with respect to the question which you have put regarding my notions of the constitution of the ether, I must confess that I am not able to give any satisfaction. One thing only I'm persuaded of, is that the constitution of the ether, if it ever would be discovered, will be found to be quite different from anything we are in the habit of conceiving, though at the same time very simple and beautiful. If you know Kyle Stanford's book, Exceeding Our Grasp, he draws pessimistic conclusions from the fact that scientists in the past, there's often an unconceived alternative that we now think is right. One thing that does happen in the history of science is sometimes when scientists are aware that they don't have a good theory for something, they'll explicitly say, quite possibly, that what the actual what's actually right is some alternative we haven't conceived of yet. Okay. Maxwell, in his dynamical theory of the electromagnetic field, he presents this sort of weird model. In this model, magnetic fields are associated with vortices in the ether. The magnetic force is along the axis of the vortex to keep the vortices from rubbing against each other and slowing each other down with friction. There's little flywheels between them. If the vortices are going the same direction, the flywheels just stay in place. If they're going in opposite directions, there'll be a net motion of the flywheels, and that's an electric current. Weird. Weird, but important for Maxwell because it was through contemplation of this model that he got the idea that there could be electromagnetic waves and got an estimate of their speed, which he estimated to be close to the speed of light. Now, what does he say about this model? I do not bring it forward as the mode of connection existing in nature, or even as that which I would be willing to assent to as an electrical hypothesis. It is, however, a mode of connection which is mechanically conceivable and easily investigated. So I would venture to say that anyone who understands the provisional and temporary character of this hypothesis will find himself helped rather than hindered by it in his search after the true interpretation of the phenomena. Okay. Then if we go now to the end or beginning of the 19th century, Lorentz, in his lectures on the theory of the electron, published in 1906, says, he starts out saying, well, everyone knows Maxwell's theory is a theory that has this electromagnetic phenomena, disturbances in some kind of ether. I must immediately call your attention to the curious fact that, about this ether, we cannot say much about it. It's true that we may represent to ourselves internal stresses existing in the medium surrounding an electrified body or magnet, that we may think of electricity as some substance or fluid, yet it must not be considered as really necessary. We can develop the theory to a large extent and elucidate a great number of phenomena without entering upon speculations of this kind. And indeed, account of the difficulties into which they lead us, speculations about the structure of the ether, there has been of late years a tendency to avoid them altogether and to establish the theory on a few assumptions of a more general nature. I'm going to say later about what assumptions he is willing to make. Okay. All right. So there's this recurrent pattern. Among 19th century ether theorists, they say, I do think the ether exists. But there's, in many cases, explicit disavowal of any kind of commitment to any detailed account of a constitution of nature. It's like, we don't know much about it. Or, McCulloch saying, I know nothing about it. Okay. Why is this important? Because the rejection of the ether is actually a major component of a lot of skeptical arguments. And here's what Kyle Stanford says about this in his book. Current physical theories regard the beliefs of 19th century optical and electromagnetic theorists about the nature and constitution of the ether to have been radically and fundamentally misguided. So I look at it and go, what beliefs about the nature and constitution of the ether? You have all these guys saying, I don't know anything about the nature and constitution of the ether. Okay. All right. Now, in Worrell's account of the pessimistic induction, there's something he calls Maxwell's theory is eventually accepted, or Maxwell's mature theory. And I just want to ask about what's the maturation date of that? When did that emerge as the way people were thinking about electromagnetism? Okay. And I think there's something, speaking totally autobiographically, there's something about the history that is systematic and misleading. So if you've taken an undergraduate course in electromagnetism, there's a set of equations called Maxwell's equations. And you also know that there's this huge treatise on electricity of magnetism by Maxwell published in 1873. And in the undergraduate course, Maxwell's equation plus the Lorentz force law basically is all you need to develop the whole theory. And that gives people the impression, I know this from talking to people, and autobiographically, I used to think this myself, that the theory we're learning in the textbook was pretty much there in place already in Maxwell's treatise. Then you read Maxwell's treatise, and you realize that is way off. Yeah. All right. Okay. And in fact, there isn't really a completed theory in Maxwell's treatise. It's very much, if you start reading it, you get the impression it's very much a work in progress. There's probably no consistent interpretation of everything he says. Notation varies from section to section. Terminology varies from section to section. Assumptions made varies from section to section. And it's not just me saying this. Oliver Heaviside, who at the time, in the 1880s, had studied Maxwell's treatise more thoroughly than anybody else had, and maybe more thoroughly than anybody has ever studied it. He says himself, I don't think there's a coherent interpretation, and there can be no finality in science in progress. Right? And Hertz said something very similar. So, for example, what we call Maxwell's equations did not exist during Maxwell's lifetime. It was Heaviside who did it. Maxwell gives you a series of equations which are, some of them involve the potentials, the A and phi, and some of them involve the fields, stuff like that. The version that we know as Maxwell's equations, which eliminates the potentials and expressed in terms of fields, is due to Heaviside. And you can sort of see why. Like Maxwell actually did, thought of the B field as the magnetic field as a derived field, and he thinks of that because if you've got a whirlpool, the velocity of the whirlpool is more basic than the vector that points along the axis of it. Okay. Okay. The relation between the electromagnetic ether and ponderable matter is obscure. One thing is clear, he doesn't have the same picture that we do. We think of magnetic fields and charged matter as two kinds of distinct things. For Maxwell, charge is some kind of condition of the ether. And by the way, he doesn't actually distinguish between ether and matter. It's been called a one medium theory. It's just, there's this stuff everywhere, and it just has different electrical property and magnetic properties from place to place. Right? But in what we think of, according to Maxwell, in what we think of as empty space, there's this dielectric medium, polarizable medium, and the D vector, the electric vector, is, which he called the displacement, is a displacement of bits of this. And if there's a discontinuity in this, say at the surface of a conductor, there's a residual charge. And he actually says, I think that is actually what all charge is. So it's not actually something that's inherent in ponderable matter. It's something that is some property of the ether. Right? In the literature on scientific realism, much is made of the fact that within Maxwell's theory, you can recover Fresnel's sine law of reflection and refraction, right? Because they both have transverse vibrations that act in pretty much the same way. It's actually not in Maxwell's theory. Maxwell, when he's treating of light propagation, it's only homogeneous media. He never talks about what happens at the boundary between two media of different indices of refraction. And if we can talk about this in discussion, there's actually a principal reason why he wouldn't know what to say. I actually think, and I've said this in an earlier paper, you actually can't get the law of refraction and reflection within Maxwell's theory. It comes from Lorentz's theory, Lorentz's transfigured version of that theory. Okay. One thing there's a danger when you're reading stuff that kind of looks like what's familiar, of not noticing the differences. And I confess that I didn't realize this until it was pointed out by someone else. He never mentions the possibility of electromagnetic waves outside the optical spectrum. Nowadays, we think of that as the most important prediction of Maxwell's theory, and Hertz's generation of long wave electromagnetic waves as a confirmation of the theory. There's actually uncertainty among historians about whether Maxwell himself was aware that his theory entailed the possibility of using an alternating current to produce electromagnetic waves outside the spectrum. no good account of the electrodynamics of moving bodies. That continued to be a open problem for many, many years. And as I've already mentioned, the modern separation of charged matter and electromagnetic fields is not in Maxwell. It's due to Lorentz in the 1890s. And actually, in some ways, it's very much not in the spirit of what Maxwell does. Okay. Okay, so I wanted to talk about when the maturation date of Maxwell's theory is. And we can get a clue from the fact that according to Worrell, the mature version of Maxwell's theory treats the electromagnetic field as sui generis, explicitly not a manifestation of the contortions of some underlying material medium. And so we should ask, when did people start saying that? Well, a few people had suggested this earlier, but the influential paper that eventually led to the acceptance of that view was Einstein's On the Electrodynamics of Moving Bodies, published in 1905, in which he says the introduction of a light ether will prove superfluous, inasmuch in accordance with the concept to be developed here, no space at absolute rest endowed with special properties will be introduced, nor will a velocity vector be assigned to a point of empty space at which electromagnetic processes are taking place. And that's the picture. Electromagnetic fields is just freestanding things in otherwise empty space that ends up in the modern textbooks. So maturation date of Maxwell's theory can be no earlier than September 1905. And of course, it actually took a while for that to be accepted by the scientific community. Why do I want to emphasize this? Because in the same journal a few months earlier, there was a paper published by the same author called On a Heuristic View Concerning the Production and Transformation of Light, in which the author argues, it seems to me that the observations regarding black body radiation, photoluminescence, production of cathode rays by ultraviolet light, and other groups of phenomena associated with the production of conversion of light can be understood better if one assumes that the energy of life is discontinuously distributed in space. So that this is the seeds of the light quanta theory. I just want to point out, Einstein doesn't think he has a worked out theory at this point. He actually just says this is a heuristic point of view. He's well aware that there is a problem of reconciling this with the well-known interference phenomena. And basically what this paper is doing is initiating a research program to construct a theory that is going to do justice both to the phenomena that he's talking about and to the more familiar wave phenomena that you get from Maxwell's theory. Right. Okay. So what Worrell calls Maxwell's theory is eventually accepted, or the mature version of Maxwell theory, it's basically the theory called classical electrodynamics in 20th century textbooks. Doesn't exist in the 19th century, doesn't exist prior to Einstein initiating this research program of constructing a theory on which there are light quanta. And if you look at what the 19th century theorists are doing, they're clearly engaged in a process of theory construction, not presentation of anything like a completed theory. Right? Why can there be classical electrodynamics as a more or less completed structure? Why is it possible in the present day for an undergraduate to take a course in classical electrodynamics whose content is pretty much the same as the content of first edition of J.D. Jackson's book from the 1940s? Right? Well, it's because classical electrodynamics is not regarded as being obligated to keep up with changes in progress in science. It's possible because that theory has been relieved of some of the responsibilities that 19th century theorists regarded as essential to a completed theory. In particular, things that are in a course on classical electrodynamics and in a standard textbook on classical electrodynamics, things beyond the scope of that theory is accounting for the structure of charged matter. That's quantum. giving a fully adequate count of absorption and emission of radiation by matter, that's quantum electrodynamics, right? Not part of the scope of this theory. Okay. I think this probably generalizes that anytime you have something like a completed or self-contained or mature theory, it's a theory that's already been superseded or otherwise relieved of certain responsibilities that one would otherwise have thought to be within its scope. Right? So the standard model of particle physics, which can be taught as a more or less self-contained unit, can be regarded as so rather than a work in progress because it's accepted it's an effective field theory, a low energy approximation to some as yet unknown more complete theory. Why does this matter? Because in the literature on philosophy of science, philosophers like to pit, they talk about theory choice. They like to pit completed theories against each other. And in the literature on scientific realism, sometimes people say, well, our ontological commitments should only come from mature theories. I think those are a lot rarer than is generally recognized. And if we accept this, it makes it easier to claim that mature theories tend to be correct within their restricted scope because we're not expecting more of these mature theories than they can, in fact, do. So I think it's a good bet. So, for 80 years, there's been standard courses on classical electrodynamics whose content has pretty much changed. It wouldn't surprise me if that was true for the next 80 years. I do hope that substantial progress is going to be made in physics in the next 80 years, but that is pretty much intact, right? Okay. And part of the matter is sometimes said that problematic shifts in ontology concern fundamental ontology. That what sometimes people explicitly say is what a theory is supposed to do is, at least the theory of physics, is tell you what the world is like at the most basic or the most fundamental level. Right. Another thing that should be uncontroversial is there not now and never has been a serious candidate for a comprehensive fundamental theory. But what I mean is a theory that tells us what things are at the most basic level of reality, a theory that doesn't come with explicit restrictions on scope. We have very, very good theories. David said yesterday that if you take the standard model plus a theory of gravitons, it's good to incredible degree of precision to incredibly high energies. We don't know how high, but we do think it's not arbitrarily high, that it breaks down at some point. Right? Okay. And there actually hasn't been anything at all like that prior to the 20th century in the history of science. Right? Okay. So on the question of ontology, we really should be thinking about ontology for non-fundamental theories, because that's what we have. Right? And so if you're thinking about ontology of classical electrodynamics, it should be compatible with thinking of classical fields as something that emerged within some appropriate regime from something quantum. When you think about the ontology of quantum mechanics, it should be compatible with thinking of quantum mechanics as a theory that emerges in a low energy limit from a quantum field theory. I think that this is the sort of thing that should be non-controversial, but sometimes in the literature on quantum mechanics, people talk as if, okay, we're going to do ontology for quantum mechanics, and you might have a non-relativistic quantum mechanics, and you might have a different ontology for quantum field theory. And I find it very difficult to make sense of that because they don't have disjoint subject matter. Ordinary non-relativistic quantum mechanics deals with, like you might, at the beginning of your course, calculate the energy spectrum of a hydrogen atom, which consists of one proton and electron. That electron is the same electron whose anomalous magnetic moment is computed with high degree of accuracy from quantum field theory. Okay. And whatever you think about the ontology of quantum field theories, it should be compatible with thinking of quantum field theory as emerging in a low energy limit from something else. Okay. Now, can we do that? There are arguments in the literature that claim that the whole historical record shows that we should be pessimistic about the ability of scientists to judge prospectively, and not only in retrospect, about what it is that is doing the real work in their accepted theories. I think if you actually look at the historical record with careful attention to what scientists are saying they're committed to and what things that they're more agnostic about, I actually think that it gives us ground for optimism about that. Okay. Last topic. I've got like 5 minutes left. Okay, great. One of the mainstays of the pessimistic induction, and regarded in some circles as the most problematic case for scientific realism, or the best case for anti-realism, is the claim that modern physics has actually abandoned the luminiferous ether. And I just want to quote a passage from that same paper by Stein. So it says, Hilary Putnam, writing as an exponent of realism, has used the notion of the ether, in contrast with that of atoms, as an example of a scientific term that failed to refer. There's no such thing as the ether, according to modern science, whereas there are atoms. Larry Loudon has exploited this as one example among others in an argument against realism. And Harry says, for my part, I throw up my hands at this. Why should we say that the old term ether failed to refer, and that the old term atom did refer? Why? That is, except for the superficial reason that the word atom is still used in textbooks and the word ether not. And he goes on to say, I could do a lengthy dialectic number on this, but in brief, our modern physics teaches us that even though there is nothing in modern physics that has all the properties that were assumed for the ether or the atoms, in both cases, 19th century physics there was a lot that 19th century got very substantially right. And what he says is, for me, the case of ether and the atom are very similar. And if I'm reading Howard correctly, I think he's suggesting that it would be better, actually, probably. We'd see a clearer relation between modern physics and 19th century physics if we'd retained the word ether. Okay. Now, that might sound nuts to you. So I'm going to make a blatant appeal to authority that might say this strains, and saying that what we have in modern physics, using the same word ether for what we have in modern physics, it just strains what ether can be. I'm going to cite 3 people. So Einstein in 1905 said introduction of a light ether will prove superfluous. We already quoted that. What is not as widely recognized is that sometime later, sometime after the formulation of the general theory of relativity, he started saying, I shouldn't have said that back in 1905. So this is from a lecture given in Leiden with Lorentz present. The special theory of relativity does not compel us to deny ether. We may assume the existence of an ether, only we must give up ascribing a definite state of motion to it, i.e. we must take from it the last mechanical characteristic which Lorentz had left it. If you remember in 1905, the reason he was saying the ether was superfluous is that we don't have to talk about velocity with respect to the ether. Right? And I like this. A little out later, he says, today, Lorentz's discovery may be expressed as follows. Physical space and the ether are only different terms for the same thing. Fields are physical states of space. And when he's talking about Lorentz's discovery, he's talking about that move that I'd already mentioned that Lorentz made in the 1890s of making a separation between charged matter and the ether. And on that version of the theory, all the ether does is is a location for electric and magnetic fields. And of course, in the 1890s, Lorentz still thinks that you need to be able to talk about your speed with respect to the ether. Because after all, you can get a wave equation with a speed built in. Speed with respect to what? Okay. And the interesting thing is that Lorentz and Oliver Lodge agree. You can find statements in both of them where they're agreeing with Einstein. It's only a terminological matter. We can talk about empty space or we can talk about ether. And there's a case to be made for Einstein's preferred choice that we actually continue to talk about the ether. In a letter in 1916 to Einstein, Lorentz explicitly says, by this time, he's accepted the principle of relativity. He was kind of a late adopter on this. He says, there can be no question of the reality of the ether. I can choose to talk about the ether if I want, and that can be useful. But there's no disagreement between me and Einstein about whether ether really exists. And the interesting is Oliver Lodge, in his own encyclopedia article on the ether, says exactly the same thing. He says it's only a terminological matter. A lot of people these days prefer to talk about empty space. I prefer to talk about ether. It's only a question about words. And the reason this is interesting is Oliver Lodge was one of the first circle of Maxwellians. So he and Fitzgerald were the first people to take up the Maxwellian research program. And so by 1926, he's the last surviving Maxwellian. And he had a real fondness for mechanical models of the ether. But by 1926, he's OK with saying, ether and empty space, we can use either word. Okay, so by the beginning of the 20th century, it's widely agreed that in the spaces between bits of ponderal matter, there are physical properties that vary from place to place, including energy and momentum. Einstein, Lorentz, Lodge, Max Born, if I keep looking, I can probably find some more people, regard as merely a terminological matter, whether we use the word ether or for space devoid of ponderal matter. And if we'd taken the advice of these people, we would now express the special theory of relativity as not saying we have abandoned the ether and electric magnetic fields are self-subsistent things in empty space. What we're saying is what we learned was the ether doesn't have the sort of structure that permits us to talk about our speed relative to it. And that is a substantive claim. So for example, if the ether had the sort of molecular structure that Maxwell was imagining in the 1860s, then there's a matter of fact, first of all, Maxwell's equations can't be exact. They're macroscopic averages over lengths that are large compared to the size of these vortices. But there's a matter of fact about if you're moving about how many vortices you're moving past per second, right? For some, if it had that kind of molecular structure, there would have to be a matter of fact about how fast you're moving with respect to the ether. But if the ether is sort of a smooth structuralist thing, or if the only properties it have is the property, electric and magnetic fields, and in the general theory of relativity, curvature, etc., then it doesn't have the sort of structure that is required to make sense of your speed relative to it. Okay. And I just find it interesting to imagine another possible world in which the physics community had taken that advice of Einstein, Lorentz, and Lodge. I mean, these are major figures in the history of electromagnetism. How would these discussions of philosophy go if we were still using the word ether? Okay. Now, some of you might still be balking at the idea that modern physics still retains an ether. And what I want to do is quote the conclusion of Maxwell's treatise, and I want you as sophisticated people who have thoroughly absorbed the lessons of 20th century science to ask yourself, and I mean seriously, ask yourself, what, if anything, do I disagree with Maxwell on here? He says, he talks about various theories, not just his own, which have energy transmitted from, through otherwise, through the spaces between bits of ponderable matter. And he says, if something is transmitted from one particle to another at a distance, what is its condition after it has left the one particle and before it's reached the other? Whenever energy is transmitted from one body to another in time, there must be a medium or substance in which the energy exists after it leaves one body and before it reaches the other. For energy, as Torricelli remarked, is a quintessence of so subtle a nature that can not be contained in any vessel except the inmost substance of material things. Hence, all these theories, not just his, but the other theories that he was canvassing, lead to the conception of a medium in which the propagation takes place. And if we admit this medium as a hypothesis, I think it ought to occupy a prominent place in our investigations, and that we ought to endeavor to construct a mental representation of all the details of his actions. And this has been my constant aim in his treatise, he says. By the way, he doesn't say he's achieved that aim. And if you're reading this at the end of having read all 2 volumes, you're keenly aware that he has not achieved that aim. Right. Okay. So according to current physics, energy and momentum is transmitted through the spaces between bits of ponderable matter. Also, mechanics can be extended to cover the dynamics of the electromagnetic field in the sense that it can be treated within the Lagrangian formalism. And eventually, that's what Maxwell meant when he said, I want to construct a dynamical theory of the electromagnetic field. I want to be able to treat it within the Lagrangian formalism. And so if you disagree with anything that Maxwell said in that previous slide, it's probably with his assertion that whatever carries energy deserves to be called a substance. This brings me to my final thesis. Substance is a technical term of scholastic metaphysics. It's not a technical term of modern science. Any disagreement over what does and doesn't deserve to be called substance is no scientific interest. Okay. Now, if we talk about the transmission, I'm almost done. Right? We talk about the transition that did occur. It was a transition from an ether that was assumed to define a state of rest to one that does not. And from the very beginning of Maxwellian electrodynamics, the electrodynamics of moving bodies was from the beginning recognized as an open problem. Maxwell doesn't say much about it because I think he doesn't know what to say. It is true that during most of the time, it was assumed that motion with respect to ether would have to play a role in the theory. And you can understand why. Like the Lorentz force law has a velocity in it. Right? From Maxwell's equation, you get a wave equation with a velocity built in. Right? Velocity with respect to what? And the eventual solution that was adopted following Einstein is that this can be dispensed with. Prior to 1905 or so, well, you can talk about the extent to which Poincaré had this idea before Einstein. I think Einstein was the first to clearly understand it. It was an unconceived alternative. And I can imagine someone coming along and trying to use this in service of a skeptical argument about currently accepted science. From time of Maxwell to 1905, there's this unconceived alternative that we don't actually need to talk about velocity with respect to the ether. Here's why I think that doesn't work as a skeptical argument. Prior to the advent of special relativity, everyone working within electromagnetism agreed that there's a problem about the electrodynamics of moving bodies. That's why Einstein can submit a paper to the journal called On the Electrodynamics of Moving Bodies. This is accepted as an outstanding problem. And there's no agreed upon approach. So, for example, Olivier Derigal, in his wonderful book, Relative Principles and Theories from Galilei to Einstein, he talks about 5 major attempts to deal with the electrodynamics of the moving bodies in the 19th century. Right? And so, in a situation like that, when you've got multiple approaches and everyone agrees that there's no satisfactory solution, we should be open to the idea there's an unconceived alternative. And that's nothing like what we have in what I'm claiming should be accepted science. Okay. Last thing. One thing I find striking about what some scientists, more thoughtful ones, say about what they're actually positing is the way they express it. So one of the things that is used in service of the pessimistic method of induction is caloric. In another paper, I have argued that we would be better off if we had not abandoned the word caloric, and that instead of saying caloric does not exist, we should say that people were wrong to think that caloric was conserved. It is conserved in thermodynamically reversible processes, which is why the assumption that's conserved did not interfere with Carnot's reasoning. but in thermodynamically irreversible processes, caloric can be generated. Here's what Lavoisier says about caloric. We're not obliged to suppose this to be a substance, it being sufficient, as will be more clear in the following, that it be regarded as a repulsive cause, whatever that might be, that separates the particles of matter from each other so that we're still at liberty to investigate its effects in an abstract and mathematical manner. That's right there in his treatise on elements of chemistry. And in all discussions about realism and anti-realism, the only one I've found to actually quote that is Stathis Bacillus. I promised you earlier that I would talk about what Lorentz says he is assuming about the ether, because he says, we don't know much about it. And what he says is, well, we should assume that in an electric field, there's a certain state of things which gives rise to a force acting on an electrified body, and which may therefore be symbolically represented by the force acting on such a body per unit charge. That's what we call the electric force. And there's a modal aspect to that, because you're attributing that to a position in space, whether or not there's a charge there. It's the charge that the force that would be exerted on a test charge if there was one there. Right. Okay. All right. And so it's a symbol for state of the medium about whose nature we shall not venture anything. That's all he's saying about what he's assuming about the ether. Is that being rejected by modern physics? Okay, now we now think about the electric force as being frame relative, but yeah, okay. I think that this is important because when these posits are about dynamical and modal properties, what would happen, what these things do, and what their modal properties are. And I think that in physics, at least, that's just totally standard. And actually, I think that that's all we know about ordinary objects, too. Anyways, and I think that in a lot of this discussion in contemporary philosophy over ontology strikes me as an attempt to fit physical theories into frameworks ill-suited for them. David Wallace has said something similar in his writings on mathematics first representations. So in literature on quantum mechanics, there's a lot of talk about primitive ontology, and it talks as if there's a two-step process. You first posit what's there, and then you posit laws, as if you can do that independently, right? What physical theories actually tend to do is posit dynamical variables and law-like relations between them. And once we have those, I'm skeptical that there are genuine substantive questions left over about what the substances are. Do they, are there what the things are? Do the things have individuality? Stuff like that is, I'm skeptical that they're actually genuine questions. Right. Okay. And I'm not the first to say that. The number of contemporary accounts of representation physics suggests that what counts as modal structure usually expressed as mathematical relations between dynamic variables. That's how I think of Wallace's mathematics first representation. If I'm wrong about that, you can tell me. Ontic structural realism, I don't think that's a good slogan, but what Ladyman and Ross say is, according to ontic structural realism, what really counts is getting the modal structure right. It's also true of what I've called the Newtonian conception of body, which you can ask me about in discussion if you want. In my opinion, all of these are on the right track. And I wrote this slide, and then I got worried about the title, because talking about on what there is too much embedded in the traditional way of talking about it. So, maybe what does and what can do. Okay, thank you very much.
We have time for questions. Do you want to start?
And
Keep your hand up.
I
will do.
So I'm enormously sympathetic.
Yes.
And in particular, I'm very all various things to say about how we think about what field theory.
Right.
But I am complacent about measure.
Okay.
I am I observe the position that physicists take towards quantum theory. I think their position is largely many people, including in some modes of you, think not complacent. They think there are profound problems inside online that the physics community is paying far too little attention to. And the families of various solutions or posits involve various relatively radical transformations. Places where the physics community does not seem to be cautious against.
Okay.
So from the point of view of someone who's not relaxed about everything wanting who is actively engaged find revisionary solutions measurement. How do you reconcile that taking things forward?
Thank you. I'm really glad that you asked that. In the version of the paper, there's actually going to be a section on this, because I think what I'm saying does actually have implications for the way we talk about so-called interpretations of quantum mechanics. Okay, so if I'm relaxed about Everettian quantum mechanics, if you think, okay, that's fine, then there's, we just accept that. Then I think that involves a fairly serious commitment. Namely, you're extrapolating the linear Schrodinger evolution far beyond the domain in which we have good evidence for it, to the macroscopic domain. And I actually think that the path of epistemic virtue is to be very cautious about that. So the big difference between Everettian and other unitary-only solutions, and say the collapse research program, is the extent to which we are going to consider, that the linear evolution is a linear approximation to something else. And I actually think and the hidden variables, I think there's good reason to think that there is something in reality corresponding to quantum states. The hidden variables approach says, yes, but there's also something more. I think that these are, among the things that we can be reasonably, we should be reasonably agnostic about and not firmly committed, which is why, in the literature on interpretations of quantum mechanics, it's often treated by, some of you may know Douglas Adams' book, Hitchhiker's Guide to the Galaxy. There's a game called, in there called Brockian Ultra Cricket, sorry. And the only rule of Brockian Ultra Cricket is pick a side and start swinging. And I'm one of the few people who have worked in foundations of quantum mechanics who hasn't really picked a side. I've written about Everett in the sympathetic vein. I've written in both critical and sympathetic vein. I've written about hidden variables theories. I've written about collapse theories. I think that where we are when it comes to what's going, what we should really say about what's going on the macroscopic level is in a position of exploring alternatives, and I'm open to the idea that what's really going on is something no one's thought of yet.
Yeah, sure. And talk about it.
Yeah.
I mean, that seems defensible.
Right.
But I'm worried in the context of talk.
Yeah.
That where you think we should be epistemic cautious is not about where the physics community mostly wants to be epistemic.
Right.
I mean, as you know, inside physics, the research programs you're talking about are from Bridge.
That's true. They're not worried about that. We can talk about why, right? Because I think motivations for not being worried about that vary a lot from physicist to physicist, but I think in some cases it's explicitly motivated by a sort of instrumentalism, which I think we should reject.
Hey, so one way of reading the PMI is that in the past we had lots of strong ontological commitments that turned out not true.
Right.
So why should
Mm-hmm.
And kind of a broad way of thinking about what you're doing is you're strengthening the notion of ontological commitment to something like thinking you've got a completed theory and not having too many doubts about that. And you're going back and you're saying, well, in the past, we just didn't have that ontological commitment. And I take it that when you go this way, you're going to get the same question about the present. Namely, is the present a time where once we get the right notion of ontological commitment, we just don't or shouldn't have that many, in which case maybe we're not getting as much realism as we thought?
Right.
Or do you want to say that, the things many realists wanted to say, a lot of currently posited entities really exist? Is your view going to get us to those?
Yes, electromagnetic fields exist, electrons, protons exist, ribosomes, chromosomes. Yeah, we have very good evidence that these things exist, and I see no reason for skepticism about those things from the history of science, because the situation we're in is not actually comparable to these allegedly discarded commitments in the past. And okay, and you said that, right, there's two kinds of things. So you talked about commitments and more or less completed theories, right? And I'm not weakening the notion of commitment. What what Fresnel and McCulloch and Maxwell and Lawrence are saying is, I have no commitments about the nature and constitution of the ether. It's not me importing a stronger notion of commitment. They're explicitly saying that. And the standard versions of the pessimistic induction drastically distorts their attitude towards those. So some might be worried, this is too weak, this doesn't really count as realism. Well, I'm not claiming I'm defending a version of realism. There are people who call themselves scientific realisms who want something much stronger than I think we can have. And I'm not claiming that what I'm giving you something is strong enough that everyone would count as scientific realism. I'm explicitly not saying I'm advocating I'm trying to sell some version of scientific realism.
Oh, thanks. Thanks for the talk.
Okay.
At the beginning,
Yeah.
Talked about observability and kind of suggested that the beauty of explaining what's unobservable is on the anti-realist, to my best understanding. So it seems to me that in contemporary physics, more than ever, we have examples of scientific facts that are unobservable in principle.
Mm-hmm.
So I think about Manchak-Malaman's theorem, strong underdetermination in cosmology, but also some people say interior of black holes, 11th dimension in string theory, hidden variables, and so on. I don't think that all of these examples are equally right, but it seems to me that in physics, you have some examples of unobservable in principle. So my first question is, in light of these examples, do you still think that the beauty of explaining what's unobservable is just on the realist or on the anti-realist, or is it also a beauty of a realist? And also, do you think that these examples can somehow be used to support your position, which is somewhere in the middle of these views?
Okay, I'm not sure what you mean by the duty of explaining the unobservable is. What I said was, I'm not going to say very much about what the distinction between observable and unobservable is, because I don't think much rides on that distinction. I'm not making use of that distinction. If someone like von Frossen, who is going to distinguish between base a recommendation of that distinguishes our ontological equipments on a distinction between observable and unobservable, that's doing real work. The distinction between observable and unobservable is doing real work for von Frossen, and so he has to say something reasonably substantive about what that distinction is. Now, so there's now the interesting, I think it's an interesting question is, so what I do claim is that in some cases at least, we can actually get good evidence about things that are not directly observable. And I think there's a real art of turning observable phenomena into evidence about things that are unobservable. Now, Malaman's theorems and J.B. Manchak's extensions of them say, well, look, all we have access to is our past light cone, and there are extensions, there are multiple different extensions of the space-time on our past light cone that are compatible with that, right? Well, yeah, okay. We shouldn't claim to know too much about what the universe is like beyond the observable part. I think that's just right. So if there are parts of the universe that we don't have much information about and never will, then the simplest thing to do is to say, okay, we've got something like on a large scale Friedman Robertson Walker thing, because that's just basically extrapolating the smoothness we observe to the entire universe. But maybe the smoothness we observe is just actually very part of very slow variation and well outside the observable universe, things are very different. Of course, that's possible. Why not? Yeah, so there's lots of stuff that we don't have good evidence about yet. There's these theorems say that there's lots of stuff that we'll never have good evidence about. That is the scientific condition. We can know a lot without knowing everything, and we really have to. It's a matter of what we can and can't know is a matter of investigation. I'm not sure I answered your question, but yeah. Okay.
I'm struggling to kind of square maybe the last third with the first 2/3.
Mm-hmm.
So I'm hoping you can clarify what the relation to is with the last third follow third, or some other relation. Because as I follow the first 2/3, the whole anti-realism realism debate looks different to me. There's no record now instant with me, and it'll never look good the same way. And oh my goodness, look at all these cases of an actual historical, pieces of building up a theory, and someone saying explicitly, here's the part that I'm not going to take seriously, or something I don't know yet, and provisional is beautiful. But then it's sort of like the last third said you go all the way to say, actually, the things that were just provisional, that's actually all we need, and we don't need to ask any questions beyond those, and we shouldn't use this old classic term of substance sort of things. And so I'm struggling because I would have expected to instead maintain the possibility as a sort of scientific norm, countenancing these questions as still good questions, but just being much more careful about when it is that we actually have good evidence for answers to them. So what are the questions we can't ask?
Okay, yes, thank you. Yeah. I understand why what I said wasn't totally clear. So thank you for that question. There's something that Stathopoulos in his book calls Maxwell's insight. And it basically, I'm paraphrasing, but he says, what Maxwell realizes, we can actually learn a lot about some physical quantity without knowing too much about, like, say, how it's realized into fundamental stuff, right? But it's also a legitimate question to ask these further questions, and sometimes we can get further information about it, right? And so it's totally legitimate for these 19th century ether theorists both to say correctly, I don't know anything about the structure of the ether, and ask questions about it, right? And when Einstein is saying, I think that ether is the sort of thing that, that such that it doesn't make sense to talk about how fast you're moving with respect to it, he's making a very substantive claim about the ether. He's making a claim that doesn't have this molecular structure, right? Right. So, and I didn't mean to get the impression that we just sort of abandon the word substance. I mean, Lademan and Ross do say everything must go, right? And fine. We talk about things as things. We talk about things as substances. I guess not much rides on what we call a substance and what we don't. That's what I play. We can talk about things. We can we can partition the world into things and say, okay, these chairs are things and stuff like that. But the sorts of questions that some philosophers would then further ask, I'm skeptical, but they're real questions. Yeah.
So your focus was mostly on the inductive part. So I read the remarks of convergent realism,
I'm sorry, I'm having difficulty understanding.
So on the PMI part,
Right, yeah.
So I read the Norden's paper, remarks of convergent a long time ago, but I remember there was another, I would say, distinct part of that argument. And that was, so he was giving a different examples, not only from physics, from geometry, from different parts, to show that if you look at the history of science, you would find many examples in which we have successful theories that are false and unsuccessful theories that are true. So he says my goal is to break the link between truth and success, which, for example, numerical argument being built on. So I think that is different from the inductive part, because you might say that people who came up with ether theory, they might themselves think that's crazy. They don't even believe in it as an ontological entity. But that might still, I'm not sure about the ether theory, but that might still be part of that theory, and that theory works. And but now we know, according to certain views of that entity, the way they think it exists, doesn't exist. So in case of ether, you explain maybe it exists in some way or other, but
no, it does exist.
But in,
period. It exists.
But in other examples, we mentioned the phlogiston, epicycle. We have many other examples in history of science and it would be hard to show that all of them, in fact, unless you want to go through all these and show every single case they in fact exist. One might say that putting aside the maturity of it and everything, as long as we have a theory that is turned out to be false or has certain entities that don't exist, but and theory is successful, we can always say the same thing about our current theories, that maybe they are successful, but there might have some false entities involved in them. So I wanted to help.
Yeah, so notice I didn't talk about theories being successful or not. I talked about things we have good evidence for and things we don't have good evidence for. And so if I take any, and I do think that after the work of Perrin, we did have good evidence for the existence of atoms, for example. And of course, Dalton had been talking about atoms since the early 19th century. Chemists throughout the 19th century gradually adopted the use of atoms, but without any, a lot of them didn't have any commitment to the existence of atoms. And there was a lot of skepticism about the existence of atoms, some of it very well founded, until after Perrin's work. And I think that Perrin's work is a good example of how you can use observable phenomena to gain evidence about the existence of things that aren't directly observable. And what it's emphatically not is, we've posited this and it's part of a successful theory, so by inference, by explanation, these things exist. It's nothing at all like the reasoning. I'm going to talk about what the reasoning is. What he does is, he gives this list of various estimates of Avogadro's number from very prima facie different phenomena. Brownian motion, Rayleigh scattering, the blue of the sky from radioactive activity, all sorts of things. And if there's no such things as atoms and molecules, of course, you're going to get numbers out of all these experiments. But there's no reason to expect these numbers to be even remotely of the same order of magnitude. And what Perrin says is, but if these things are actually counting something, if these estimates are actually counting something, then they have to. So what you have is you've got something that is virtually guaranteed to be true if the atoms and molecules exist, and would be very surprising if they don't. And I think a lot of scientific reasoning is, in fact, of that form. But notice, so I think the problem is with a lot of this discussion of realism and scientific realism is this abstracts from the actual content of the claims being made. And it says, okay, we're not going to talk about what these theories actually say. We're just going to say these were successful, these are unsuccessful, and we don't even ask about what evidence people had or reasons they had for making some kind of inferences. I think that's absolutely essential. So I actually don't know what success means in Loudon's version. The theory of crystalline spheres was successful. What does that mean? Yeah, so people have this sort of image that, yeah, I posit something, it's part of a theory, it saves the phenomena, and that plus some virtues, license inference. So that's not at all the picture I have of scientific inference. And as a matter of fact, you can go through most of these cases. Did the ancient astronomers have good evidence for the existence of these crystalline spheres? Well, they explicitly say themselves that they don't. Some ancient astronomers explicitly said, it's not our job. We don't know. What's going up on the heavens is beyond our ability to actually know. And what we should do is come up with some scheme that saves the phenomena. That was known as the compromise of Geminus. Right? So I think that the sort of thing in Loudon, like it zooms out way too far. It lumps a whole lot of different kinds of things under success. And it just means success, as far as I can tell, was popular for a while or something like that, right? That's not at all what I'm talking about. Yeah. But, I'm sorry, you're going to have to speak up a lot. We've got a fan going. Yeah.
So in this case, what you want to show is that the physicists that were doing cultural dynamics were actually agnostic about the real nature of the corpuscle, implies the ether in what way. So it's unjustified to take this case as a sort of instance, as an inductive base for pessimistic materialism, because they were appropriately agnostic. But then even within electrodynamics, you could say that, for example, they believed that fields are continuous, let's say. And later, now we know that we need to make them discrete, do quantization. So there is something which they believed but turned out to be false, even within the electrodynamic work. So what this tells me is that in certain situations, scientists were indeed appropriately agnostic, and that pessimistic method induction is like the inductive base was too broad, it was mistaken in this case. But in many other cases, even within electrodynamics, they were not sufficiently agnostic. And even for things which were in the sort of appropriate domain, or even like now from this sort of perspective, contemporary perspective, constructed domain, they were mistaken in many of the cases. Right. So my question is, do you want to say that pessimistic match induction is somewhat weaker and that it just doesn't work for this case? Okay. Or do you want to sort of undermine? Okay. Yeah.
So on my picture of epistemic virtue as a mean between excessive caution and excessive credulity, you do expect that people will sometimes err on one side or another. And actually, any given research community will probably have some people who are excessively bold and people who are excessively cautious. I actually think that Einstein was, lucky, but he erred on the side of excessive boldness, and Lorentz was excessively skeptical, and that's fine. But in order to work as a source of skepticism of my order to work as an argument for skepticism about currently accepted science, it has to be an argument that people are routinely drastically overly confident. And you said that they're committed to the electromagnetic field being continuous. I wonder about that, and here's why. In your standard electromagnetic course, there are the free space fields, E and B, and then there's the fields in matter, D and H. And the fields in matter are treated as smoothly varying things, but they're averages of fields over dimensions large compared to the molecular dimensions. And so it's explicitly, we don't think that these are smoothly varying things. They're actually, on a microscopic level, they vary a lot. Okay, right? Maxwell doesn't make a distinction between free space and matter. All fields are like the fields in matter. They're averages. Like Maxwell thinks that the ether or he suspects. He says it's probably molecular, right? And so all the fields are in fact macroscopic averages over some finer grained structure that we don't know about. So that's how everybody in the Maxwellian tradition is thinking about it. Now it is true that this comes as a surprise, and that's a radical claim in 1905. That I'm sorry, I went to Einstein. I'm sorry. Okay. Here we go. That's a radical claim, and it took a while for it to be accepted. This claim that certain phenomena associated with the production or conversion of light can be understood better if one assumes that light is continuously. So I'm not saying that we shouldn't expect any surprises, but I am saying that there are areas where we have good evidence, good reason to think, good evidence that the account we have is basically right. And notice, the phenomena he's talking about involving certain processes of absorption and emission of light are areas that no one thought they had a good theory of. And there are areas where one could a reasonable person could say, surveying everything that's already out on the table, I think a very reasonable person could say, it's quite likely that what's actually going on here is some unconceived alternative. Right? That's always possible. You can be aware that you don't have a good theory of something. Right? I don't think we're in the situation like that for classical electrodynamics or quantum field theory in the domains in which they apply. We don't have reasons to think we don't have a good theory of that. And so I think in those cases, we can reasonably expect, there might be, with QFT, there might be surprises at higher energies, but the basic structure of the QFTs that we have within the energies they're well tested is going to remain.
So, thanks. You said that physical theories basically give us a model structure, certain mathematics, and also that views according to which metaphysical distinctions that go beyond that are nonsensical, are going in the right direction, if I understand correctly.
Right, so I'm skeptical that there are genuine questions about some of the things that some philosophers concern themselves with.
So it's not just that it's very difficult to gain knowledge about these distinctions, but they are just nonsense. So my question is, why do you think that? Is it because of arguments in favor of structural realism, or is it something else?
What I'm saying is something like what people call structural realism is probably on the right track. I don't really like structural realism as a slogan. So Stephen French in his book, I don't know if it is really fair to Stathis, but it attributes to Stathis a very object-oriented realism, the notion that the world consists of objects and properties, and we need to say what they are. And he says, well, Stathis does think that it's okay to say the ether is real. The word ether just refers to the word ether just refers to electromagnetic fields. And then French poses as a supposed problem for Stathis, and I'm not convinced this is fair. But how does he know that the electromagnetic field is an entity? I don't know what that question is. Once I know, once you tell me that there are electromagnetic fields and there's a certain amount of energy and a certain amount of energy and momentum, and here's the laws. Yes, but is it an entity? I honestly don't know what that question is. I'm not asserting that I have a clear demarcation between sense and nonsense, and I can say definitively that no sense of that can be made. But if someone wants to try to make sense of it, you actually have to tell me what that question is, because I honestly do not know what that question is.
So this has come up in responses to the questions as well. We have said repeatedly that, for instance, we have good evidence that electrons exist, or good evidence. So my question is, what's your conception of evidence, and whether lots of because you could think that lots of debates on realism, anti-realism might just depend on what people consider to be good scientific evidence to be.
Yeah, so we need a good account of scientific reasoning, scientific inference. I tend to think in broadly Bayesian terms. Notice that the way I expressed Perrin's inference, a moment ago was, here we have these results of measurements, and there's an agreement between these various estimates of Avogadro's number that would be possible if there's these things are not, if there's nothing to count, but would be incredibly surprising, very unexpected. And in the back of my mind, I'm thinking in Bayesian terms. But however you cash out scientific inference, it has to do justice to things like that, right? And the reason I'm saying is a lot of philosophers want to cast out scientific inference in something like hypothetical deductive terms, you posit something, you make predictions, the phenomena might falsify the prediction, but if the phenomena are compatible with your prediction, you say, okay, confirmed, right? And then that leaves you with lots and lots of different hypotheses with the same deductive consequences until you bring in extra empirical virtues to decide. I think that's got nothing to do at all with the way scientific inference works. So here's what I will emphatically deny. In some circles, it's said that all hypotheses compatible with a body of evidence are equally well supported by it. People say that. I don't think anyone's ever believed it, because it's the essence of statistical hypothesis testing that you've got a number of hypotheses, and no matter what happens, no matter how the experiment comes out, all those hypotheses will be compatible with the result, because you compute this likelihood, which is a non-zero probability of that result conditional on the hypothesis. Is nonetheless false that the evidence equally supports every hypothesis. So I think the picture people have, and this is why I made this sort of remark about Fresnel, is you got phenomena, you just sort of posit something, and you say, okay, this posit explains the phenomena, then it's well supported. And so one thing that I'm going to do when I write this paper is actually go through Fresnel's reasoning, because he actually is saying, like, what do this phenomena actually tell us about the nature of these vibrations? And he actually makes a good case that they are transverse vibrations, and that when you split a beam into opposite polarizations, the vibrations are at right angles to each other. Right? And similarly, like my colleague at Western, Bill Harper, has written a book on Newton's reasoning. And what he's doing is taking observable phenomena and turning that into evidence about the forces. It's not I hypothesize inverse square law and that works. So I think that's right. He's actually showing how you can use the laws of motion to turn the observed evidence into information about the force laws.
Discussion.
Yeah.
David, why don't you
Yeah.
have that question?
Yeah, okay, it's pretty quick.
Okay, go for it.
I mean, I'm very sympathetic to the claim about it being sort of historical contingency in the ether.
Mm-hmm.
And I didn't explain a possible reason for that. I mean, Minkowski came up with such a sexy alternative. I mean, as soon as the way you're describing it, and this seems reasonable to me, ether stripped of its mechanical and rest properties,
right.
just synonymous.
Yeah.
Space-time is such a good.
Yeah.
It surprised me.
Right.
That was the term, wouldn't you? Henceforth, space
Right.
time and ether.
Okay. Yeah. So there, yeah. So good. I like the word. I like the term space-time too, right? And so I'm actually like where did I have that quote from Einstein? Right. There we go. Yeah. Physical space and ether are only different terms for the same thing, because it's not mutually exclusive choice, right? Yeah, so we could be talking about space-time and say, ether and space-time are mutually, are just different terms for the same thing. I think that would be good. Yeah, and that actually is a real discovery, because these 19th century people had no notion of space-time, or a glimmering of the notion of space-time, and they weren't thinking of ether and space as different words are the same thing. So, yeah. So yeah, I actually, if I had my druthers, we'd be still freely using both words.
We're going to be sitting here. Thanks very much. So now we invite you to go to the 11th floor. We have a reception for when you're all welcome to join us.
Oh, I forgot. Who is the person on the